Yes, thank you very much. Now, what's expecting you? I hope an interesting presentation from agricultural machinery, starting with the agenda. I'll introduce the company Krone to you briefly, who we are, what we do, then motivation and goals of our project, then the system requirements when we started it, and then Mr. Grüppen will continue, who is to a large part in charge of this product, hardware and software structure, process reliability, and at the end, we'll give you a conclusion. Who is Krone and what are we doing? Krone is a family-owned company founded in 1986 as a small blacksmith's company. 110 years of history to the company, fourth generation now. What's Krone do? Many know it from commercial vehicles, the typical things that you see on the roads, but we're also in agricultural machinery. This is a brief overview of what the machines are that we are producing. What is it that we all make? We're a full liner in harvesting technology. We do everything from disc mowers, rotary tillers, rotary rakes, transport technology. You see rotary bales, square bale machines, forage harvesters, and mobile pellet harvesters. That's the whole line. So much for us. What actually made us start this project? I can continue seamlessly with respect to my previous presentation. We see that we have 201 different models that we make. That's quite a lot. In particular, since we have different variants to every model as well. A rotary pellet harvester is not a rotary pellet harvester. They're different in France and here, for example. So you can see that the great diversity of modules can be a challenge. And in particular, we are not selling hundreds of thousands of units, but we are selling maybe a few thousands, or sometimes only a few hundred machines, down to tens of machines, and some machines are only sold 1 unit of. So we cannot have a test stand for each and every one of them. We have to make sure that we get a modular system in place with which you can cover almost everything. So, for this project, we focused on machines that are pulled. We have also self-drive machines, but we are not talking about those now. So, and you can see at the top, we started with the round baling machines, the round balers. Another point that's important here is the so-called ISO bus. The ISO bus is a data bus, a communication protocol based on the CAN bus, based on ISO 703. What does ISO bus mean in agricultural in practice? It means that, for example, I buy a machine from manufacturer A and a tractor from manufacturer B, and they can actually talk to each other. I buy a terminal by manufacturer C, with which I can operate my machine from manufacturer A. I buy a joystick from a different manufacturer again. I've got a GPS application that I also bought in for my steering system of the tractor. You see a tablet at the very top. There's a task controller, order management. This is connected to the machine by way of Wi-Fi. Could be any system to document the data, and I'm directly connected to the management information system via the internet, and we can also monitor at all times what the driver is actually doing at that very moment. And we try to cover all this by way of our test stand. The V model, very briefly, where are we? We have the module tests here, which is done in our development at the first function test on the ECUs at the top. We have the overall system test on the machine. We did a validation on that, and that's my part of work. We are starting here with our test stand in order to support the system test, but also when it comes to integration, testing, and module integration testing, that should be also supported. In summary, what does that mean? What do we want to achieve? We want to have quality improvement of our products, of course. Then we want to be able to cope better with the complexity, the different manufacturers, the ISO bus. All of this needs to be able to be tested properly. Expectations are growing from the customers, and today's pharma is not the same as they were 10, 15 years ago. We want to respond faster to the market development. And obviously, when new demands come from development, we want to be able to respond in a flexible way. We can't say, we test it in 1 year's time. No, we have to do it right away. Legal requirement, ISO 25119 for agricultural machinery, that needs to be complied with as well. System requirements. What are the rough system requirements that we get from validation? To Mr. Grüpp to set machines up. We want to reproduce a complete machine. What I was saying before, we want to have complete machines, not just individual functions and features, but I want to be able to test the entire machine. Easy handling. The person being on the test case level, we've got a layer system, and I'll talk about that, so we've abstracted it. The people handling the test cases shouldn't be having to worry about what's happening at the bottom of the hardware level, so easy handling is important. Then, of course, extensibility is important. The system must be able to be extended very quickly. As soon as new functions are integrated into the machine, we need to be able to test quickly. Again, this is achieved by our layer model. Stability is very important. We've got an extensive error reporting system, fault alarm system. So if a test is run at the very top, this is monitored through all the levels to the very bottom, and then the feedback goes to the top whether the tests were also all of them carried out properly without any faults in the test system. And last but not least, we have process reliability. I was showing you it before, the left and the right branch of the V model. On the left-hand side, we've got the requirements, which we've documented in Polarion. On the right-hand side, we have vector VT system. How do I get that connected? How do I get the process reliability? And this is something that we had to deal with, and Mr. Grüppen is going to talk about that in more detail in a minute. That was it from me. Now I can hand over to the expert, who is going to explain the system to you. Well, I looked more at the technical aspects. I was in charge of setting the whole system up and doing the implementation. I should like to talk to you about our layer model that we've developed on our own. That shows you the entire setup of the test system. We've got 5 layers, 2 hardware layers, which are mapped by real ECUs, as is normal by Hill systems. And then we have the VT system. On top of this, we have a software layer implemented in Canoe and in VTest Studio. And I want to talk a little bit more in detail about the individual layers. So we'll start with the 2 hardware layers. We've broken them down into 2 racks. One is the ECU rack, which contains all the ECUs of the pulled Krone machines. On the other side, we have the VT rack. There we have the VT cards, 51 of them altogether that we used. Then in the ECU racks, we've got so-called junction boxes. If you set something like this up, you have to have specific wiring, which has to find a place as well. So we've decided to do this on the ECU rack so that the VT rack can be used for other application cases. And in addition, on the ECU rack, we have an ECU and CAN interconnection, which ensures, by way of relay cards, that each ECU can be connected with each voltage group, but each ECU can be configured for each CAN channel. And all of this plus the VT cards give us the opportunity for every condition and every pulled Krone machine to be mapped by way of this hardware system. Another benefit is that we also wanted, when it comes to changing different machines, we wanted not to have to do any change in the hardware configuration. So this change goes entirely via the software configuration. I've got two pictures here of the two racks. On the left-hand side, you see the front view, and on the left-hand side, the VT rack with the 51 cards, and the ECU rack with the ECUs. On the right, you see it from the back. This was in the prototype phase yet, so the connectors are one-to-one connections, but we gave them connectors in such a way that we can use the rack for other applications as well. Coming to the first software layer, that is the ECU level. This is an interface that we've defined ourselves to the hardware. So basically, it's a map of the real ECUs, an image of the real ECUs. So per real ECU, we've got an image of that. So if you make a setting on one of the ECU, configure one input, you configure a certain voltage, multifunction input. One should be so and so many volts. That is set on this level, and this level plus the VT system will ensure that this is also set automatically on the real ECU. What are the benefits by way of this level? On the one hand, we are making it easier to overview, because we are focusing on the Krone specialties. So the things that are prohibited by the VT cars that we don't have an application for will be taken out at this stage. Then we have the possibility of intervening upstream of the hardware. Is to say, we can remove, we can do without the hardware, and can, for example, do a rest bus simulation. And then per ECU image on this level, we've developed a panel, on the one hand for monitoring of the set events, but also as a user interface. You can see it here. You can see in practical terms that this is one of our ECUs. You see the multifunction inputs 1 to 7. And on these multifunction inputs, for example, I can configure a constant voltage, and I was mentioning before, the system will ensure that the same thing takes place and can be detected on the real ECU as well. So we'll go one layer up, the machine layer. This is the heart of our testing system, because here we have the concrete machine, which is meant to be used for the tests later on as well, is being put together here. And we can see here, while we're on the ECU level, we're talking about inputs are assigned certain voltage levels. On this level, we have a kind of abstraction level where states are converted into physical quantities, and the tester can actually talk to the system. Since a machine normally has a number of sensors and actuators, we tried for the wide spectrum to be summarized in function groups. When it comes to the calculation for these sensors of the states shall be transferred to the physical value, such as voltage, and we'll put this together in a component library in order to make it easier to overview it, but at the same time make the system more flexible. Two examples: it's an inductive sensor. On this level, can actually take the fault states, like a broken cable, but also a damped and undamped state, and it will then work on the higher level with this condition, with this status. This is a linker sensor. Here we have an angle sensor, where we've parameterized certain angles. What else do we need for our machine structure? The interfaces. So we've got components on this level, but generally speaking, they are configured for a certain ECU input or output. This is also done on this level here. One component is assigned a set of interfaces. From the higher level, the maximum configuration of the machine that evolves here can be then transferred to a certain variant of the machine. Just like on the ECU level, we've developed panels here per machine. So here I've got an example for a round baler. because this is what we started with in our project. You can see an excerpt, and you can see the voltage groups that can be switched at the top, which ensured that the individual ECUs switch themselves onto the correct voltage groups. And then you have this example here of an inductive sensor, of a closure hook of such a baler. And you can see the different conditions, damped and undamped conditions. One layer up further, that's the so-called test level. It maps the abstract view of the safety system. Here, this is the level on which the tester will actually operate. As I was mentioning before, from this level also we make sure that the maximum configuration of this machine is then transferred to a certain variant of configuration. In this context, we also made sure that for machine sequences that are the same across several processes or machines, that they are summarized in the functional library, so that when it comes to maintenance, we can reduce the maintenance efforts and make it easier to keep an overview of it. This is an example from VTest Studio that we're using. You see some test cases for the round baler. And again, that was another important point. Here we made sure that the test developer who uses this level is given as high a degree of freedom as possible, so that from this maximum configuration he can actually transfer it to any specific variety that he wants. In order to make it more easy to understand for you, I've got you an example. You see all the levels together here at the bottom. These are the real ECUs, which are mapped by the ECU rack, the VT modules, which are mapped by the VT module rack, the ECU number 1 level, the machine level, and the test level. And my example now is a round baler sequence, so we're selecting one certain test, the round baling pressing test. The machine level is then transferred to this variant, which makes sure that the system is initialized on the ECU level. Certain connections are made, or the information is passed on to the VT modules, which in turn will make sure that the hardware is actually configured in that way for the machine. You see the reference to the function, to the component library. That's part of the initial condition and status. And we are also referencing from the component library the corresponding calculation. So this is a reduced example now. So a certain status is set. For example, we simulate the bale size of 200 centimeters, which is assigned to the system in the test. This information is then passed on to the machine level, machine layer. Then on the panel that I mentioned before, can be used. It can be monitored by way of this panel, so that it's reliable. As the next step, then this component will reference to the component library where the conversion is made. Constant voltage of 402 volts. And here on the correct input, on the ECU1, input 2, you would see here that there's a constant status of 4.2 volts that was set there. As mentioned at the beginning, this level makes sure that the correct VT module is addressed in the mapping. And this again ensures, by this cabling connection, that the real ECU can actually detect this very same voltage at its input. At the beginning, my colleague was talking about process reliability as being one of our requirements, and I want to take a closer look at this and how we actually did it in concrete terms in our situation. Going back to the V model, and basically this is about how we get the link link between the left branch to the right branch in place. So for writing the requirements, we use Polarion, and we are using VTest Studio to implement the test cases. For this purpose, we are using Polarion Connection Utility tool, which enables us from Polarion to load the requirements into VTest Studio, where we link them up with test cases, and this link can be uploaded to Polarion again, and in Polarion we've got an interlink to the various requirements. If we then do the test procedure, the tool enables us for this report to be written back as a test run in Polarion, and then we've got a link also to the test cases and also to the requirements. And then finally, we come to the conclusion. What is it we've reached, that we've achieved so far? So we've concluded the basis of the test system. The structure is prepared for all of our machines, just like the ECU level. So for ECU that we have in the level has already been implemented in the test system. For the round balers, we have implemented fully automated tests. We are using it for basic diagnostic test and also for flash bootloader test as a sideline. And our next steps, what are we planning to do next? We want to roll it out. That's to say, we want to map further machines in the test system, but we want to go further in depth as well. That's with respect to the isobus. We want to improve our test coverage, buzzwords here being the task controller, the tractor implement management, and the universal terminal. And there's more that might come up as needed. Thank you very much for your attention, and if you have any questions, we shall be happy to answer them. Thank you. Thank you very much.